Hello everyone, and welcome to the final lecture for the Organic Chemistry Lab. So in this lecture, I'm going to be going over nuclear magnetic resonance, or NMR spectroscopy. So in the previous labs, I've kind of already touched upon NMR of the different chemicals, of the different compounds we've made during the whole semester. So now I really just want to go more in depth and give you guys an idea of what NMR is, how it works, and why we use it specifically. So NMR spectroscopy is the most commonly used technique for determining the structure of an organic compound because it's useful in identifying the hydrocarbon skeleton to which different functional groups is attached. So remember that in previous examples, what would happen is we would be able to look at an NMR and kind of figure out which pieces of the molecule belong where, and then from there we can stitch the molecule back together. So NMR is a very useful tool in kind of figuring out the different functional groups or figuring out the different pieces and then finally making the entire molecule from the NMR spectrum. What's very useful about it is that it requires very small amounts of product and it's non-destructive. And we can obtain large amounts of information such as the number of protons in the molecule, the relative positions of the different atoms we're looking at in the molecule, and we can even measure different nuclei such as these isotopes like carbon-13, fluorine-19, or phosphorus-31. In the lab, the type of NMR we mostly used was proton NMR, and this allows us to kind of qualitatively and quantitatively characterize the different types of hydrogens in the molecule. We can also use different types of NMR, such as carbon-13 NMR, or fluorine or phosphorus, but this really depends on how many of these atoms are in the molecule we're studying. So remember that all nuclei have some kind of spin state, whether it is positive or negative 1/2. And when these, due to these spin states, they actually generate a magnetic field. Normally, this magnetic field is quite random, but if we were to apply an external magnetic field, such as this magnetic field H0, we're able to align the random spins into some kind of parallel or anti-parallel that follows the magnetic field that we've applied. So we can see that all of the magnetic fields are facing in the same direction, but they're going either in the positive or the negative 1/2 state. So the frequency of absorbed electromagnetic radiation is different depending on the element, as well as different isotopes of the same element. So NMR is concerned with changes in the direction of the spin orientation. And so this is what nuclear magnetic resonance is. And this occurs as a result of the absorption of radio frequency radiation. The frequency of these absorbed electromagnetic radiations for a particular nuclei depends on the molecular environment of the nucleus or its electronic environment. So if we were to apply all the protons with the same magnetic field, they should absorb at the same frequency. However, when a molecule is subjected to some kind of magnetic field, the bonding electrons circulate in a way that generates some additional weak magnetic fields of their own. And these new magnetic fields that have been made kind of oppose the large magnetic field that we're inducing. And so this can shield the nuclei of other nuclei in the molecule. So the greater the shielding, the lower the frequency required to produce resonance. So for the proton chemical shifts, these shifts are a measure of the degree in which a nucleus in a molecule is shielded. And you'll see these when we look at the NMR spectrums. So protons in different environments are shielded to greater or lesser degrees, and because of this, they will show up different on the NMR due to their chemical shift. To really understand how these molecules or how these nuclei shift, we use a reference standard, or tetramethylsilane. So the protons of which are more highly shielded than the protons of most other organic compounds. So TMS will usually be the 0 that you see in an NMR spectrum. So here we have the graph of an NMR spectrum. Towards the left is 10, towards the right is 0. So when we move towards the left, we are saying that we're more downfield, so we are experiencing decreased shielding. If we're moving towards the right, we're moving upfield with more increased shielding. And so you can see here that at 0, we will have our TMS standard. So remember that the chemical shifts are measured in ppm, and they're always going to be measured relative to our TMS standard. So depending on the electronegativity of substituents, this might decrease the shieldings of various methyl groups. So you can see here that we have 5 different electronegative groups. And as we kind of go from least electronegative to more electronegative, we can see that there is a greater shift. So at 0, we have our trimethylsilane. If we were to use ethane, we would expect to have a C in the absorbance at around 0.9 ppm. And then once we start adding more electronegative atoms like nitrogen, it'll go up to 2.2 ppm. Oxygen will go to 3.2. And trimethylfluorine is 4.3. So a good way to kind of remember, the more electronegative the atom, the greater the shielding, or the less shielding that will occur, and it will be moved more downfield. So this effect is cumulative. So the more of these electronegative atoms we have, the less shielding we should see. So starting with trimethylchlorine, we can see that we get around 3.1 ppm. Adding another chlorine takes it to 5.3. And then finally, methyl trichloride will be at around 7.3 ppm. So another, I guess, key important fact is that protons that are attached to sp2 hybridized carbons are less shielded than those attached to sp3 hybridized carbons. So that means when we look at ethane versus a double bond versus a benzene ring, what we should expect is that this sp3 hybridized hydrogens should appear at about 0.9. This double hydrogens attached to the double bond will appear at about 5.3, and the hydrogens at a benzene ring that is completely hybridized will be at 7.3. So what kind of information do we actually get from looking at an NMR spectra? So the 4 pieces of information that we should be looking at are the number of signals that we receive, because this tells us the different types of hydrogens that appear in the molecule. Where exactly these signals appear, so they let us know what types of hydrogens we have. The relative area under the signals, or the amount of hydrogens that we have of each type, as well as any splitting patterns that let us know how many neighboring hydrogens exist. And so you'll see what I mean as we go further and look at some examples. So first, the number of signals. So first we want to see the number of different types of hydrogens that appear in the molecule. So we have a couple examples that we're going to be going over more in depth later on, but just to kind of quickly go over these. So here we have cyclohexane, and every carbon on this cyclohexane will have 2 hydrogens. So every single hydrogen here is equivalent. Moving on to this molecule, we can see that every hydrogen is kind of blocked off on its own with no neighboring hydrogens. So every hydrogen here should be exactly the same, so the same type. Here we have a benzene ring. It's exactly the same as cyclohexane, but instead of 2 hydrogens coming up from every carbon, it's only 1. So every hydrogen on this ring is equivalent to the other. And on here we have dimethyl benzene. So remember that the hydrogens on the benzene ring will be equivalent. Meanwhile, the hydrogens on the methyl groups will be equivalent to each other. So we'll have one type here and then another type here. So a couple more examples. So here we have 3 groups of hydrogen. However, they are all the same type because they all kind of share the same symmetry and are equidistant from each other as well as from the bromine. So they are all the exact same hydrogen type. If we were to linearize the molecule and have ethyl bromide, we can see that this hydrogen is different from this hydrogen because it's feeling more of an electronegative, or it's feeling more of that electronegativity from the bromine. So these 2 hydrogens are not equivalent, so we have 1 and 2. If we were to add another methyl group to the end, then we would have 1, 2, 3. Now what if we were to move this bromine right into the middle? We would have a symmetrical molecule down the center. So because this hydrogen and this hydrogen are equidistant from each other, they are the same type. However, the hydrogen in the middle, because it has 6 neighbors, so 3 hydrogen here, 3 hydrogens here for 6, and it's the closest to the chlorine, will be its own type. A couple more examples. So if they were not symmetrical, we should expect 4 different signals. So we have the hydrogen that is closest to the bromine. We then have the hydrogen that is in between, and then the hydrogen the furthest away, and then another hydrogen that only has 1 neighboring hydrogen. So we have 4 different groups right here. If we were to have a linear molecule with chlorines flanking both sides, so this is propyl dichloride or dichloride propane, what we'd expect is this molecule is symmetrical. So same like the previous example. These 2 hydrogens should be the same. Meanwhile, this one that is in the dead center should be different. So here we have a very interesting case. So we have 1 hydrogen group here, another hydrogen group here that is feeling an effect from chlorine, so these 2 are different. And then because these are on a benzene ring, these are all actually the same signal. And so you'll see when we look at the NMR spectrums of these molecules, what I mean by that. So remember that the position of these signals kind of tell you what types of hydrogens there are. So primary hydrogens will have a 0.9 ppm, secondary is 1.3, tertiary is 1.5. Hydrogens in an aromatic is 6 to 8.5. Hydrogens of an allele are 1.7, and then in a benzyl is 2.2 to 3. And then these can shift depending if we add some kind of halogen, such as chlorides, bromides, or iodides, and they're usually around anywhere from 2 to 4. And then alcohols will also affect the position of these signals. So here I kind of have a table that gives I guess, examples of some more widely known functional groups, or more widely seen functional groups that can appear on molecules. And while we could try to memorize exactly the locations of all of these functional groups, I think it's more important for you to understand how, I guess, different parts of the molecule have an effect on other parts of the molecule. So it's better to understand of like how these hydrogens are affected based off of electronegativity, whether they're on a benzene ring, or how far away they are from the center of the molecule. So from there, you can kind of, in a way, guesstimate where the peak should be, and this should help you kind of figure out what molecule you're working with when you're looking at an NMR. So here's like an example of toluene. So toluene is made up of one benzene ring as well as a methyl group. So this methyl group will have its own signal. Meanwhile, all the hydrogens on the benzene ring will have their own signal. So we should see two signals, A and B. Because these hydrogens are a primary hydrogen, we expect them to be more upfield, closer to zero. Meanwhile, the hydrogens on the benzene ring, because they're on an aromatic, on an sp2 hybridized carbons, we expect them to be more downfield up here at 7. So here's just, I guess, like an example of what I was talking about, of like the different types of hydrogens. So just running through these again. Cyclohexane, all the hydrogens have one signal. For this molecule, because they're on their own with no neighboring hydrogens, and it's completely symmetrical, they all have one signal. Benzene, one hydrogen on each point, one signal. Dimethylbenzene, benzene has its own signal, and then the methyl groups have their own signal because they're equivalent. For this molecule, we have 3 groups of hydrogens that all share the same signal because the molecule is symmetrical and all of the methyl groups are equidistant from the bromine. For the ethyl bromide, we see that there are 2 signals, one from the one furthest away and then the one closest. If we add another methyl group, then it's 3 signals, going from farther, middle, to closer. If we have the chlorine move towards the middle, the molecule becomes symmetrical again, and so the methyl groups at the end are one signal, and the hydrogen in the middle is another. And then if we look at this unsymmetrical one with bromine, we can see that there are 4 different hydrogen groups. For the propane that's flanked by 2 chlorides, it is symmetrical, so the 2 hydrogens have the same signal, and this hydrogen has a different signal. And then finally, for that weird one, we see that the methyl has its own signal, the methyl chloride has its own signal, and then the benzene ring shares the signal with its 4. So the next step, the next key information that we can receive is the integration, or how many hydrogens appear in each type. So let's go back to that propyl bromide. So we can see that we have 3 different types of hydrogens, and for each type there are different amounts of hydrogens. So in type 1, we see that there are 3 hydrogens that belong to this type. In type 2, there are 2, and then in type C, there are 2. So the integration would be 3, 2, 2. But if we were to move this halogen right into the middle so that the molecule is symmetrical, and we have 2 groups that are the same, that means we have 6 hydrogens in type A, and only 1 hydrogen in type B, so 6 and 1. So going over the same molecules, because there are 2 hydrogens on each point, the integration for this molecule is 12. Meanwhile, for benzene, because there is only 1, the integration is 6. So because all of these methyl groups are exactly the same, and there are 4 methyl groups, we can see that there are 12 hydrogens of the same type. For this molecule that has the benzene ring, we know that the benzene ring each has 1 hydrogen, so 4 for benzene. And then the methyl groups, there is 3 on each side, so 6 for the methyl groups. For this molecule over here, again, same thing. We have 3 groups of methyl groups. So 3, 6, 9, 9 hydrogens. When we linearize it, we have two different types. So there are 3 hydrogens in type A and 2 in type B. Adding another hydrogen adds another type. So 3 for A, 2 for B, 2 for C. And then, like we saw in the previous example, if we make it symmetrical, then we have A that has 6 hydrogens because they're the same type, and B that has 1 hydrogen. Continuing on, because we have 4 different types, we see that A has 3, B has 3, C has 2, and D has 1. Moving to this symmetrical molecule, we have A and B. So A has 2, and B has 4. And then our final molecule, we have our benzene ring, or what's left of the benzene ring, that has 4 hydrogens. We have our methyl, which has 3, and then our methyl chloride, which has 2. So by integration, we're kind of just talking about how tall the peaks are. Something else you'll see on an NMR spectrum is splitting. So you can see that here we have one line, but in these other examples, we could have 2, 4, 5, and this all really depends on the amount of neighboring hydrogens that exist in the molecule. So the more common splitting patterns are singlets, doublets, triplets, quartets, and quintuplets. And the splitting is higher than any splitting that is higher than this is usually called a multiplet. So our splitting patterns usually follow the n+1 rule, where n is the number of neighboring protons that are at least 3 bonds away. So if we look here and we have our hydrogen that has no neighboring hydrogens. So this is 1, 2, 3. There's no neighboring hydrogens 3 bonds away. It is a singlet. If we add 1 hydrogen that is a neighbor, so 1, 2, 3, it becomes a doublet. Adding a second hydrogen, it's a triplet. And adding 3 hydrogen, it is a quartet. So in general, the n equivalent neighboring hydrogens will split a proton signal into an n+1 Pascal pattern. So remember, neighboring means that they cannot be more than 3 bonds away. So if n is the amount of neighboring hydrogens, this n+1 is the signal that we get. So if there are no neighboring hydrogens, then we expect a singlet. If there is 1 neighboring hydrogen, then it is a doublet. Then we go to 2 neighboring hydrogens, triplet, 3 neighboring hydrogens, quartet, and then quintet. So just remember that n must be equivalent neighboring hydrogens to give rise to a Pascal splitting number. If the neighbors are not equivalent, then you will see a complex pattern. So this is a complex multiplet. So the alcohol hydrogen, or in the OH group, usually does not split neighboring hydrogen signals, nor is it split. And it'll normally be a singlet of integration 1 between 1 to 5.5 ppm, and this can vary depending on the molecule. So here we have our cyclohexane. So because they're all the same signal, we see that they are a singlet. For the next molecule, because they don't have any neighboring hydrogens, this is also a singlet. For the benzene ring, same as cyclohexane, singlet. For this dimethylbenzene, we have our benzene group, which is a singlet, and then our methyl groups that share no neighboring hydrogens that are also singlets. Using that same theory for this molecule over here, because they don't share any neighboring hydrogens, they are singlets. So here's where things get different. So we have 2 types of hydrogens. This type A has 2 neighboring hydrogens, and type B has 3 neighboring hydrogens. So because type A has 2, 2 plus 1 is a triplet. And because B has 3, 3 plus 1 is 4, which is a quartet. Moving on to this next example. Following that same logic, A has 2 neighboring hydrogens. So 2 plus 1 is a 3, so triplet. C has 2 hydrogens, so 2 plus 1 is a triplet. And B has 3 plus 2 neighbors, so 5 plus 1, which is 6, making it complex. If we have this symmetrical molecule here, we can see type A has 1 hydrogen, so 1 plus 1 is a doublet, and B has 3 on each side, so 6. So 6 plus 1 is 7, which is a septet. So again, A, 2 plus 1 is triplet, 1, so for B, 1 plus 1 is a doublet. For C, 3 plus 1 is 4, plus 1 is 5, which is complex. And then D, same thing, complex. For the symmetrical molecule, for A, 2 plus 2 plus 1 is 5, so quintet. And then for B, 2 plus 1 is a triplet. And then for this molecule over here, since they have 3 different signals, A is a singlet because it doesn't have a neighboring hydrogen. 2 is also a singlet because, again, it has no neighboring hydrogen. And then the 4 on the benzene ring are also a singlet because they are on a benzene ring. And so when we have an alcohol, remember that the hydrogen on an alcohol will usually appear up as a singlet. Our methyl group, 2 plus 1 is 3. All right. Yeah, 2 plus 1 is 3, so a triplet. And then for B, 3 plus 1 is 4, quartet. All right. So now let's actually look at the NMR spectrums so we can see what they look like. So here we have our cyclohexane, which appears as a singlet. And remember that these are sp3 hybridized. So they should appear a lot more upfield than on the benzene ring. Again, sp3 hybridized, each one having its own group. We expect a singlet of about 12 hydrogens. So really tall peak, singular peak. So benzene ring, because these are sp2 hybridized, they will appear more downfield, but they are still a singlet. So for that dimethylbenzene or p-xylene, we expected 2 signals. So let's start with our methyl groups. Because they're sp3 hybridized, they should be more upfield. They should have a singular peak because they are singlets. They have no neighboring hydrogens. Meanwhile, the hydrogens in the benzene ring, they are also singlets, but they should be more downfield. So next is tert butyl bromide. So each group had its own, so each group is by itself with no neighboring hydrogen. So they all share the same type of hydrogen. So because they have no neighboring hydrogen, they are a singlet. And because they're sp3 hybridized, they're more upfield. So now we can go on to a more complicated example, ethyl bromide. So again, all of these hydrogens are sp3 hybridized, so we expect them to be more upfield. So the group that is further away should be less shielded and should be more downfield. So more closer towards the left. So this methyl that should, wait, other way. I am so sorry, flip that the other way. So because this methyl group is further away from the bromine, we expect it to be more upfield. Meanwhile, this hydrogen that is closer to the bromine should be more downfield because of the shielding effect. So going with A, so A has 2 neighboring hydrogens. 2 plus 1 is 3, so a triplet. So here you can see 1, 2, 3. There's our triplet. Meanwhile, for B, it has 3 neighboring hydrogens, so 3 plus 1 is 4, quartet. 1, 2, 3, 4. So this group belongs to this methyl, this peak belongs to that methyl. So now 1 bromopropane. The same logic applies. The closer you are to bromine, the more towards the left you are. The farther away you are, the more towards the right. So starting with A, the furthest away, we have 2 neighboring hydrogens, so 2 plus 1 triplet. There's 1, 2, 3. Starting with the next one would be the closest one, which has 2 neighboring hydrogens, so a triplet, 1, 2, 3. And then the one in the middle, which has 5 neighboring hydrogens, which makes it a complex. So we expect 1, 2, 3, 4, 5, 6. So the one in the middle is our, I guess, the middle group. So for isopropyl chloride, so we have our first type, which is the methyls on the outside. So because they share 1 hydrogen, or because they have a hydrogen as a neighbor, 1 plus 1 is 2, so we expect a doublet. And you can kind of see the doublets. They're really close together, but this is a doublet. Meanwhile, the type B, which is 1 hydrogen that has 6 neighbors, so a septet, can be right here. And so what's really important for us to notice here is the integration. So this group only has 1 hydrogen, so the peak is smaller, versus this group, which had 6. So for 2-bromobutane, let's start with A. We have 2 neighboring hydrogens. 2 plus 1 is 3, triplet. For B, we have 1 neighboring hydrogen. So 1 plus 1 is 2, which is a doublet. For our C, it has 4 neighboring hydrogens. Yeah, 1, 2, 3, 4. 4 plus 1 is 5, which is complex. And then D, 3 plus 2 plus 1 is 6, another complex. So for the more complicated molecule, orthomethyl chloride, we have 3 signals. So our signal A has, So our signal A, which is a singlet, has no neighboring hydrogens. We expect it to be right here. No. Right here. Okay. So, orthomethyl chloride, which you can see here, has 3 signals. And so we can easily differentiate which signal is which by the integration, because all of them are singlets. So we have the higher the integration. So this is our 4 hydrogen integration, which is for the benzene ring. No. All right, so for the next molecule, we have orthomethyl chloride. So this molecule has three different signals, A, B, and C. So the first thing we want to look at is the benzene ring, because remember, these are sp2 hybridized. So we expect them to be more downfield around 7. So this peak should be our benzene ring. So what's left now are the methyl groups, this lone methyl group, and then the methyl group bound with a chlorine. So because this hydrogen in B is feeling an effect from the chlorine, it should be more downfield than the other methyl group. So this should be C, B, A. And that makes sense because remember, this integration is higher than this integration. All right, so now we have ethanol. So let's start with A. So A is the furthest away from the OH group. It has a signal of, it has two neighboring hydrogens, making it a triplet. So because it's the furthest away, we should expect it to be this peak. 1, 2, 3. B is our OH group, and remember that OH groups are usually singlets, so we can find them right here. And so that leaves the last peak, our quartet. So C has three neighboring hydrogens, plus 1 is a quartet. So 1, 2, 3, 4. So now here's an example. Look at ethyl benzene and determine how many different types of hydrogens exist and which peaks they belong to. All right, so for ethyl benzene has three different types of hydrogens, one for our benzene ring, and then one each for these two methyls. So let's begin with the easiest one, benzene. Because they're sp2 hybridized, it should immediately be this peak here. Moving on to A, so A has two neighboring hydrogens, plus 1 is a triplet, and because it's the furthest away from, I guess, the molecule's periphery, we expect it to be this one. So 1, 2, 3. And then we have the hydrogens in the middle. Because it has 3 plus 1 is 4, is a quartet, and so it should be this smaller peak right here. 1, 2, 3, 4. So what about p-diethyl benzene? So p-diethyl benzene has three signals. As you can see, it is symmetrical. So A, B, B, and then whatever is left is the C. So again, easy peasy. The C should be this ring, should be right here at 7. Meanwhile, the molecule A should be the one at the periphery because it's the furthest away. So I'm assuming it's this one. Let me make sure. Hydrogen is 2, plus 1 is 3, triplet, 1, 2, 3. And then same thing for B. Because it's slightly more towards the middle of the molecule, we expect it to be toward a little bit more downfield. So 3 neighboring hydrogens, 3 plus 1 is 4, 1, 2, 3, 4, a quartet. All right, so what about 2-bromo, 2-methylbutane? So we can see that there are 3 different groups or different types of hydrogens. We have these 2 methyl groups that are close to the bromine. A CH2 that's about the same distance, but that is also bound to a CH3. So let's go over this one. So the easiest one to kind of do is A because it's the furthest away. So it has 2 neighboring hydrogens. 2 plus 1 is 3, triplet, 1, 2, 3. And then we get into this little mess right here. So these are 2 different types of hydrogens, but because they're really close to each other and really close to this bromine, their signals overlap a bit. So let's look at B. So we have the 3 hydrogens here that do not have a neighboring hydrogen, because that, if it did, it would be right here. So these are on their own, so they should be a singlet. So this really tall peak is our singlet. Meanwhile, this hydrogen here that has 3 neighbors, so 3 plus 1 is 4, is a quartet. You can kind of see them here. So 1, 2, 3, and then the 4 would be kind of right here. So we can, so signals can kind of overlap on each other depending on how the atoms are arranged. So now let's look at di and propyl ether. How many signals are there? Or how many types of signals are there? And which signals belong to which type? So we can see that they are actually symmetrical. So we have 3 different signals going from, I guess, inward to outward, C, B, A. So let's start with the easiest one. So it's always easier to start, I guess, further away from the molecule, or further away from the electronegative atom, which is our oxygen. So if this is our oxygen, we expect that these hydrogens on the outskirts should be the most upfield. So CH3 has 2, so it should be a triplet. So it should be 1, 2, 3. Meanwhile, this CH2, which is a little bit towards the middle, it has 5 neighbors. So 5 plus 1 is 6, so it's complex. So 1, 2, 3, 4, 5, 6. And that leaves C as our last set of peaks, which is 2 neighboring hydrogens plus 1 is a triplet. 1, 2, 3. And now let's look at propanol. So starting from the I guess the hydrogens furthest away, CH3, it has 2 neighboring hydrogens. 2 plus 1 is 3, triplet. 1, 2, 3. B, it has 3 plus 2 plus 1, which is 6, so it's a complex. 1, 2, 3, 4, 5, 6. So C is our singlet, because remember, alcohols are singlets. So here is the alcohol. And then finally D, which is a triplet because it has 2 neighboring hydrogens. 1, 2, 3. So here is the NMR of benzaldehyde. So you can see that there are, so for benzaldehyde, there are really 2 types of signals where the signals on the benzene ring are really, really close to each other. But we can see that the hydrogen on the aldehyde is the, I guess, the most downfield because it's close to the carboxyl group. As well, and then the hydrogens on the other side, on the benzene ring, so the hydrogens that are closest to the benzene group will have a higher ppm than this hydrogen furthest away. So you can see 7.89, 7.64, and 7.73. So here is one of benzoic acid. You can see that because of the carboxyl group, that we can kind of distinguish between HC, HA, and HB, where the signals can kind of separate a little bit. So here is another example that you can kind of work out. So for isopentyl acetate, how many signals are there and where do these signals belong? So though that is everything I have for proton NMR. The last bit I have is just a bit on carbon NMR. So carbon NMR utilizes this specific isotope of carbon, carbon-13. And carbon-13 makes up about 1.1% of all carbons. And it's a completely stable isotope. It's found like in nature. So it can be found in about 1.1% of all molecules that have carbon in them. So it's the same thing as proton NMR. We check the number of signals for the different types of carbons, the splitting to show the number of hydrogens on the carbons, any chemical shifts that occur due to hybridization, as well as any chemical shifts that occur due to the environment. So for here, we have 2-bromobutane. So we have 4 different signals because each carbon here is affected differently due to this bromine. So yeah, like I guess for other types of NMR, the main theory still applies, but instead of using hydrogen as the atom that you're studying, you'll be using carbon or fluorine or phosphorus. But that's really the general idea of how NMR works.